Hello everyone. Today we're diving into an incredibly cool topic: ground launch assist systems. Have you ever wondered why we still use traditional methods to launch rockets instead of cutting-edge technologies like maglev or vacuum tunnels? This idea isn't exactly new, it's been proposed for quite some time. Today, we'll break down these high-tech solutions step by step to see if they're actually viable and why they haven't become mainstream yet. When it comes to ground launch assist systems, the concept didn't emerge only after modern rocket technology matured. In fact, even before modern rockets existed, people had already envisioned using ground-based devices to propel objects into space. You might recall the early sci-fi classic From the Earth to the Moon, featuring scenes where humans are blasted toward the moon via giant cannons. While the film's absurdities like carrying umbrellas to the moon or encountering eerie faces on its surface are well known, the core concept of ground-assisted spaceflight had already taken root. By the 1950s, this concept was put into practice through the High-Altitude Research Project HARP. They constructed a 36-meter-long giant cannon capable of launching a 41-centimeter diameter projectile to an altitude of 180 kilometers. Technically speaking, this did propel an object into space. However, the project faced two critical flaws. First, the projectile could not achieve orbit. Even if it reached space, it would eventually fall back to Earth due to gravity, unable to maintain stable orbit. The second problem was the extreme acceleration required. The projectile had to go from 0 to nearly 8,000 kilometers per hour in just 0.03 seconds. Generating a gravitational acceleration of 7,500 gigaseconds. This force would destroy not only humans but even the most delicate electronic equipment. In essence, these early attempts were humanity's search for a more affordable means of space access. However, the engineering capabilities and understanding of space physics at the time were insufficient to overcome these bottlenecks. Nevertheless, these explorations were not entirely without merit. They at least highlighted acceleration control and orbital velocity acquisition as core challenges that must be resolved. When discussing modern ground-based launch assist systems, spin launches, Centrifugal launch system stands out as a truly innovative solution. Instead of catapulting rockets from a cannon, they install a massive centrifuge within a vacuum chamber. Rockets are secured to the device, which spins at high speeds to accumulate kinetic energy before flinging the rocket free, effectively replacing traditional rocket boosters. Furthermore, their electric-powered system is not only environmentally friendly but also reusable, potentially significantly reducing costs and offering vast potential. Currently, Spin Launch has constructed a 33-meter diameter, 1/3 scale demonstrator at its New Mexico spaceport and successfully test-launched 10 rocket models, with the highest reaching nearly 10 kilometers in altitude, initially proving the technology's viability. Furthermore, in April 2025, they announced plans to advance the Meridian Space Constellation project. Collaborating with a Lithuanian company, they aim to mass-produce microsatellites, with an in-orbit demonstration scheduled for completion in 2026 and deployment beginning in 2027. The ultimate goal is to build a constellation of 1,200 satellites dedicated to providing broadband services. However, constructing the full-scale system is far more complex. They plan to build a 100-meter diameter full-scale facility in Alaska, aiming to accelerate rockets to 8,000 kilometers per hour. During this process, the rocket will endure extreme gravitational acceleration. The carbon fiber tethers securing the rocket must operate at 60% of their material strength limit, leaving minimal safety margin. More critically, both the rocket ejection timing and the vacuum door opening must be precise to the millisecond. Even the slightest deviation could cause the high-speed spinning rocket to collide with the chamber wall, resulting in mission failure. Additionally, the moment the rocket is ejected, the previously balanced centrifugal device suddenly loses equilibrium and must rapidly restabilize. This places extremely demanding requirements on the control system. Although Spin Launch claims its full-scale system can deliver 200 kg payloads into orbit at half the per kilogram launch cost of SpaceX. These technical hurdles are far from trivial. The extreme payload environment and ultra-precise control demands long-term technological breakthroughs. Final success hinges on the outcome of their in-orbit demonstration scheduled for 2026. For a deeper dive into this technology, check out the related videos on real engineering, featuring on-site visits and detailed technical breakdowns. Truly fascinating. In fact, beyond spin launch's approach, many have considered adding ground-based auxiliary systems to existing rockets like the Falcon 9, Starship, or Falcon Heavy. However, actual calculations reveal these options consistently present a high investment, low return scenario, offering extremely poor cost-effectiveness. Take the widely recognized Falcon 9 Block 5 rocket as an example. Based on the latest 2026 data, its maximum payload capacity for low Earth orbit in ocean recovery mode is 17.5 tons. With a launch weight of 549 tons and 9 engines in the first stage, it achieves a thrust-to-weight ratio of approximately 1.41 to 1. Some propose installing a 70-meter-long magnetic levitation launch rail to achieve a net acceleration of 3g. These would increase takeoff velocity by 41 meters per second and boost payload capacity by roughly 300 kilograms, a mere 1.7% improvement. While this sounds promising, the energy required to achieve this goal is staggering. Generating 3g of net acceleration requires auxiliary systems to deliver 26g of thrust, equating to 14 meganewtons of force. This demands 980 megajoules of kinetic energy equivalent to 270 megawatt-hours of electricity. Moreover, this energy must be released entirely within 2.15 seconds, requiring a peak power of 450,000 kilowatts equivalent to the combined peak power of 562 Tesla Model S vehicles. If powered by superchargers, this would require connecting 1,800 250 kilowatt chargers simultaneously, a clearly impractical solution. Compounding the challenge, the rocket's exhaust plume reaches extreme temperatures during launch, risking the destruction of mounting brackets, magnets, and wiring harnesses. Pre-igniting the engines to counteract this would increase zero-gravity ignition risks and compromise performance. A genuine dilemma. Now regarding the Starship system, according to SpaceX's latest 2026 data, the third-generation Starship measures 123 meters in length and employs a two-stage design. The first stage features 33 engines with a takeoff thrust of 75.9 million newtons. The second stage has 6 engines and a low Earth orbit payload capacity of 100 tons. The previously mentioned 150-ton figure was an early theoretical value that has since been revised, utilizing a 140-meter-tall launch tower to provide 3g of net acceleration would enable a velocity of 54 meters per second, increasing payload capacity from 100 tons to 103.3 tons, a 3.3% gain. However, the corresponding energy demand is staggering. 17,080 megajoules of kinetic energy equivalent to 5,000 kilowatt-hours of electricity must be released within 3.1 seconds. This requires a power demand of 5.5 gigawatts, nearly equivalent to the full output of 6 medium-sized nuclear power plants. Even with massive capacitors for energy storage, the required scale remains enormous. Furthermore, high-voltage cables could be scorched by rocket exhaust triggering arc discharges that render the entire scheme practically unfeasible. Some have proposed replacing the electrical system with pulleys and counterweights. However, calculations show this would require 175,000 tons of counterweight, roughly the weight of 2 Ford-class aircraft carriers, with steel costs alone reaching $175 million. Moreover, supporting such immense weight would demand extremely complex structural designs for pulleys and launch towers, making it fundamentally uneconomical. Consider smaller rockets like Rocket Lab's Electron, standing only 18 meters tall with a fuel capacity of 13,000 kilograms. Its modest scale seems better suited for ground-based auxiliary systems. One proposal involves constructing a 1-kilometer vacuum maglev tunnel, propelling the rocket at 5G acceleration. Throughout the journey, this would increase payload capacity from 300 kilograms to 375 kilograms, a 25% boost. This solution requires approximately 177 kilowatt-hours of energy, with a power demand under 100 kilowatts equivalent to the electricity from 400 supercharging stations, making it more manageable than the previous two proposals. However, constructing this 1-kilometer vacuum maglev tunnel could cost hundreds of millions of dollars. Its development cost of approximately $500 million delivers 43 times the launch capability of the Electron rocket, far surpassing the 25% payload increase achievable through ground support systems. Therefore, adding ground-based auxiliary systems to existing rockets, investing substantial funds for only limited payload increases offers extremely poor cost-effectiveness, rather than expending significant effort developing complex systems. It is simpler and more efficient to directly build larger rockets. Beyond augmenting existing rockets with auxiliary systems, some have proposed entirely abandoning rockets in favor of transporting objects into orbit via giant vacuum maglev tubes. While this idea sounds wildly ambitious, it is fundamentally unfeasible. The concept involves constructing an ultra-long vacuum maglev tube, placing a Crew Dragon spacecraft inside, and accelerating it directly into low Earth orbit through the tube. To ensure human tolerance, acceleration is capped at 5G, with a target velocity of 7,500 meters per second. The remaining velocity would be provided by the Dragon's own thrusters. From a purely physical standpoint, achieving this velocity would require a 573-kilometer-long vacuum tube, roughly the distance from Taipei to Kaohsiung, extending nearly horizontally to facilitate orbital insertion at the exit. Additionally, massive support structures would be needed to hold up this 100-meter-tall tube. Such an enormous project would incur astronomical construction costs and inevitably take years to complete, making it fundamentally unrealistic. Regarding energy requirements, accelerating the 12,500-kilogram Dragon spacecraft to 7,500 meters per second demands a total energy input of 351,000 megajoules, equivalent to nearly 97,500 kilowatt-hours of electricity. This translates to an average power requirement of 23 gigawatts, sustained for 15.2 seconds. This represents the total electricity consumption of 2 million average households in just 15 seconds. Existing power grids are simply incapable of delivering such immense instantaneous power. More critically, energy requirements scale quadratically with velocity. Maintaining constant acceleration demands exponentially increasing power. For instance, accelerating the Dragon spacecraft from 0 to 50 meters per second requires only 15 kilowatts. But accelerating from 7,450 meters per second to 7,500 meters per second demands 4.5 gigawatts. Such extreme power fluctuations are beyond the capacity of existing energy supply systems. However, recent technological breakthroughs in miniaturization offer hope. In January 2026, research by the International Astronautical Federation revealed that compact electromagnetic launchers can now accelerate a 10-kilogram payload 2225 kilometers per second using just 30 kilowatt-hours of electricity. This achieves a launch cost per kilogram below $100 and enables 10 launches per minute. Domestically, institutions are constructing a 1,600-meter ultra-high-speed elevated vacuum tube maglev test line, though current focus remains on rail transit applications rather than space launch. Thus, full-scale rocket-free vacuum maglev tube launch systems remain impractical for now. While miniaturized electromagnetic launch solutions may prove useful in specific scenarios, however, replacing traditional rockets remains a long-term goal. At this point, some may ask, if it doesn't work on Earth, what about the Moon? With its low gravity and lack of atmosphere, Could the moon be suitable for developing ground-based launch assist systems? This idea holds merit, but practical implementation presents significant challenges. The moon's gravity is only 1/6 that of Earth, approximately 1.63 meters per second squared. With an escape velocity of 2.38 kilometers per second and no atmosphere, these characteristics do reduce the complexity of a ground-based launch assist system. For instance, entering lunar orbit requires only 1.02 kilometers per second velocity, far less than the 7,800 meters per second needed for low Earth orbit. Returning from the moon to Earth would also require only a 2.38 kilometers per second velocity increment. Furthermore, the moon and Earth are tidally locked, enabling the construction of a permanent orbital device that always points toward Earth. This setup theoretically allows returning objects to Earth without consuming propellant. Sounds pretty cool. However, practical calculations reveal significant challenges. Maintaining 5G acceleration to reach the 2.38 kilometers per second return velocity requires sustained acceleration for 48.5 seconds, covering nearly 58 kilometers. This necessitates constructing a 58-kilometer-long orbital acceleration facility. The lunar surface presents harsh conditions, extreme temperature fluctuations, and rugged terrain. Constructing such an extensive track would be exceptionally challenging and costly. Furthermore, the energy requirements are staggering. Accelerating a 12,500-kilogram Dragon spacecraft to return velocity demands 35,000 megajoules of energy, equivalent to 9,700 kilowatt-hours of electricity, requiring an average power output of 668,000 kilowatts. Establishing such a large-scale energy supply system on the moon, whether solar or nuclear, presents a monumental challenge. Consequently, in the near term, lunar ground-based launch assist systems cannot support crewed returns to Earth. However, for transporting resources like helium-3 or lunar regolith, higher acceleration launches could be considered. Considered to reduce payload mass, thereby lowering energy requirements and orbital length. Should future lunar mining operations become frequent, making round-trip transportation more common, this approach might gain viability. Currently, SpaceX plans to use Starship for Mars exploration by late 2026, with lunar-based technologies also under development. However, ground launch assist systems remain absent from near-term plans, indicating persistent practical obstacles to their implementation. After exploring various alternatives, the core conclusion remains clear. Traditional rockets will remain the optimal orbital launch choice for the foreseeable future. This explains why ground-based launch assist systems have yet to gain widespread adoption. First are the cost and energy consumption issues. Whether retrofitting existing rockets with assistive devices or constructing rocket-free vacuum tubes, both require building massive infrastructure and significant capital investment. Additionally, the energy demands are staggering, far exceeding the capacity of existing power systems. Even supercapacitors struggle to resolve issues of instantaneous power and stability. More critically, despite massive investments, payload capacity increases are limited at best, only 25%. In contrast, building larger rockets like Rocket Lab's Neutron, costing just $500 million, can boost launch capacity by 43 times, offering vastly superior cost-effectiveness. Second is the issue of flexibility. Once ground-based assist infrastructure is built, it becomes extremely difficult to modify, should future requirements call for larger rockets or modified launch parameters. This infrastructure becomes obsolete and hinders technological advancement. Traditional rockets, however, offer flexibility by adjusting fairing size, engine count, and fuel type to adapt to diverse launch needs, with technological evolution independent of fixed infrastructure. Moreover, decades of development have established mature technical systems and industrial chains for traditional rockets, with reliability and safety rigorously validated through extensive practical application. For instance, the Falcon 9 Block 5 model has achieved high-frequency reusability, while Starship has completed 11 flight tests and achieved key technological breakthroughs like booster recovery. In contrast, many core technologies of ground support systems such as millisecond-level control and structural stability under extreme acceleration remain in the exploratory phase. Only miniaturized electromagnetic launch solutions have made some progress in specific scenarios, but they have yet to undergo sufficient validation through actual orbital launches. It really boils down to the KSS principle. Keep it simple, stupid. Building a slightly larger rocket is often simpler and more feasible than investing heavily in complex ground-based launch systems. Of course, if space launches become as frequent as airplane takeoffs and landings in the future with multiple spacecraft entering orbit hourly combined with breakthroughs in miniaturized electromagnetic launch technology, then large-scale ground infrastructure might finally become a worthwhile investment. But for now, space launch frequency remains far below that threshold, and traditional rockets retain their irreplaceable advantages. Ultimately, humanity's exploration of ground-based launch assist systems aims to push past the physical limits of rockets and discover more efficient, cost-effective pathways to space. While the concept is sound, current technological and economic constraints make these solutions unfeasible for the time being. Thus, for the foreseeable future, traditional rockets will remain the mainstream choice for orbital launches. Today, we've covered a lot about ground-based launch assist systems from the early HARP supercannon to modern centrifugal systems like spin launch, along with various proposals and lunar scenarios. I hope you now understand why these high-tech solutions haven't gained widespread adoption yet. Finally, I'd like to ask, if you were designing a launch system from scratch, would you choose a traditional rocket or a ground-based assist system? Feel free to share your thoughts in the comments section. That wraps up today's content. Thank you for watching. If you enjoyed this episode, don't forget to like, subscribe, and share. See you next time.